This is a video on the normal force. I know I already introduced it and we talked about it kind of extensively, I guess, but the problem is that we've only really talked about it in terms of a horizontal surface with a same mass. But that's not always what happens. The normal force is not just equal to the mass times gravity. It's not equal to your force of gravity all the time. The normal force does what it needs to do to cancel out the forces and keep things from accelerating up or down. Normal force is a lot like static friction in a way, because it doesn't give you the gravity force all the time, but it can if it needs to. The only thing is you can't really overcome the normal force, but what you can do is you can overcome all the bonds in between, like a tabletop. Say if you put something too heavy on a table, those will break, it'll shear, and that's a little bit different than overcoming a normal force. But in the sense it is, I guess. Okay, so normal force part number 2. We had talked about stuff on a horizontal surface, and we know that if we have an object resting on a horizontal surface, force of gravity will act down, and our normal force will act up, and it will counteract those two things. So when we have this happen, obviously it's not going to accelerate. Again, we don't accelerate down into the table or up off of the table. If we do, that analysis is something that's pretty complicated. So here we'd assume that our acceleration is 0, and that means that our sum of forces is equal to 0, and therefore our normal force vector plus our force of gravity vector is equal to 0. And again, to be like proper about this, we should call it the 0 vector, but that's kind of just a trivial thing. It's really only important for mathematicians. For our purposes, we can just think of it as just being 0 for our vector equation. And what that ends up resulting in is that when I take my directional parts out of my vectors, so we go from our vector world to our scalar world, we get a positive normal force, again, defining up to be positive y, and maybe right to be positive x. We have a positive normal force and a negative force of gravity. So negative is our direction, and F sub g, this piece right here, is our magnitude. It's the number that tells us how long our force of gravity vector is. And that is equal to 0. So again, by adding the force of gravity to both sides, I will get a normal force is equal to force of gravity, again, by using Newton's first law. However, there's a lot of times where we have some problems with this. This doesn't work out perfectly when we talk about inclined planes. So if I have an object or an inclined plane, and I place an object on that, let's say our angle of incline is only 15 degrees. So there's my mass I place on it. Gravity, the force of gravity, always acts down towards the center of the Earth. There it is, force of gravity down. However, our normal force does not always act up, directly up. Normal force is called the normal force because normal in mathematics doesn't mean average. It doesn't mean it's what you expect it to be. It means it's 90 degrees from the surface. And if our surface is inclined at an angle of 15 degrees, this thing is still 90 degrees to that surface. And so our normal force here points perpendicular to that surface that's inclined at a 15-degree angle. As you can see, this is not going to perfectly cancel out gravity, and there's going to be a part of gravity that's going to be pointed down the inclined plane, and part of it that will be pointed in the direction of our normal force. So here's that part in the normal force direction. So you know what, let me do that in a different color. So here in blue is our part of our gravity, which we'll call maybe FGY. Since we're used to normal force being in the y direction, we'll call this piece of gravity vector in the y direction. Actually, I drew it a little bit too long. About to there. That looks a little better. Okay, a little bit better. And that force of gravity vector, that is in the y direction is what's going to be equal to our normal force, not the overall force of gravity vector, because there's a component. Oh, wow, that went fast. There's a component of FGY that points in this direction as well, right? So if I take my two vectors, there's a component of the force of gravity that points in that direction, not of FGY. If I take my force of gravity in the x direction, force of gravity in the y direction, and I do that vector addition stuff that we talked about a while back, and did a tip to tail addition, basically this is what I would get. I would start off going down this way in the y direction, out this way in the x direction, and what I get is my f of g that I draw from the tip of the first vector to the tail of the second vector. But that worked out well for us when we did worksheets in our normal Cartesian coordinate system, but now it's not going to work out for us as well in this Cartesian. Here's our positive x in this direction, positive y is up. This doesn't work very well because our normal force is pointed in two different directions, both the x and the y direction. Our friction force, if we had one, sometimes we do problems with frictionless surfaces, but our friction force will point parallel to our surface, probably up the incline. And so that means our friction force is also going to be in the x direction and the y direction, right? So there's a component that points this way and a component that points this way. And so these two vectors would have to be decomposed into our x and their x and y components if I wanted to do an analysis on this situation. And that would leave us with a fkx, an fg in the y direction, and a n sub x, a normal force in the x direction. Also, in the y direction, we'd have an ny, we have an fky, and then we'd also have that fg. So what's going to happen is there's going to be two things that we have to decompose, at minimum two things, because if there's a second mass pulling it down, or if I'm exerting some sort of force to push it or pull it down, at the same time, it's going to also have to decompose that force. So at minimum, you will have to do two decompositions of vectors if we use the x, y, horizontal, vertical coordinate system. So it's not exactly useful for us to use that coordinate system in these inclined plane scenarios. What is useful is if I go up or I could say positive y is perpendicular or 90 degrees to the surface, and positive x could be up or down, but either way it has to be parallel to that surface. If I do it this way, now you can see that my friction force is no longer in two different directions. It's entirely parallel to that surface, and so it's entirely in the x direction. Same goes for my normal force and being entirely in the y direction. My force of gravity, I still have to decompose that, but it's the only vector I will have to decompose. If I exert a push force or a pull force or something like that, it's going to be canceled out in the y direction by the normal force and fgy, and so there'll be no acceleration. I don't have to worry too much about that stuff. But in the x direction, it's going to be entirely parallel to the surface. So I will not have to decompose any push, pull, whatever vectors, or really do any significant work to make that easier for me. So again, just to restate what I'm trying to say, if we use our horizontal and vertical coordinate system, then we have to decompose two or more forces. If we use a rotated coordinate system that points down the incline or up the incline, then we will only have to decompose at most one force. So this is why we do our thing. And remember, through the law of similar triangles, the angle of incline, which we will call it theta, angle of incline is also this angle in our FG vector diagram that we drew here below our mass. So our normal force now is not going to be equal to FG, right? This will not happen. The reason why is because if I look in my new Y components or my new Y rotated coordinate system, I'd say my sum of forces in the Y direction is equal to 0. Again, I'm not going to see this thing accelerate into the inclined plane or just spontaneously float up off of the inclined plane. Instead, what I'm going to see is it have that same horizontal, new horizontal, I guess, the new Y direction distance. It's not going to go up or down from that distance off of the inclined plane. So my forces are going to add to 0. In this case, I will have a normal force, and we'll go ahead and make those vectors. I'll have a normal force vector plus a FGY vector, and this is FGY. So this is a little bit harder to think about because in the previous problems that we've done, in the first unit, we had, say, maybe we projected an object, it has a velocity v, and we gave it some angle theta, and then we said that Vx is equal to v times cosine theta, and Vy is equal to v times sine theta. Here in this world, we're not giving an angle with respect to the x-axis. In our kinematics, we gave angle theta WRT, which means with respect to an x-axis. In this world, this angle right up here, circling it in blue, that angle is given with respect to a y-axis, right? Here's our y-axis, the angle is somewhere down here, and so yes, we are given an angle with respect to a y-axis. What that does is it flips our sines and cosines with x and y. And so it's pretty clear if you draw the triangle out, and we'll just scroll down and do that. Here's our adjacent leg, here is our opposite leg, and here is our hypotenuse. There's our angle theta. So my adjacent leg is going to be in that y direction. And so we would say that this is FGY, and it is equal to, let me erase that and redo it in a bigger, so you can see it. That is our FGY, and it is equal to FG times cosine theta, because it's an adjacent leg. And this right here is going to be our FX in our rotated coordinate system, and it will be equal to FG times sine theta. And so you see our FX gets a sine theta, and our FY gets its cosine theta. Going back to our vector equation over here, I have normal force is equal to, or normal force plus FGY force is equal to 0. Again, these are vector quantities, so if we pull out the directional components, we get our normal force minus the force of gravity in the y direction magnitude is equal to 0. This tells me that my normal force is equal to my FGY and not just FG. And I can relate that to FG using FGY equals FG times cosine theta. And of course, FG itself is mg. So I get mg cosine theta is equal to my normal force, ultimately. This is one of those situations where if I have an inclined plane, I will have a normal force that will equal to mg cosine theta instead of just mg. But wait, there's more, because it doesn't have to be just mg cosine theta. It could be capital MG, or it could be m1 m2g plus, or m1 plus m2 times g times cosine theta. It could be a bunch of different things, because when we add mass to an object, it also changes our normal force. When we exert a force on an object, up or down, it will change our normal force. So I'll give you another example of that real quickly. So first example, if I have a block, again, let's say it's mass 1, and we know that this is again on a horizontal surface, and the force of gravity points directly down, it's equal to m1 times g. And let's say m1 is equal to 5 kilograms. I have another mass, m2, it's half of m1, and it's 2.5 kilograms. If I take m2 and I place it on top of m1, it's going to exert a norm or a friction force down. Or not friction force, excuse me. It's going to exert a gravitational force down. It's hard to see, but that's an m2. And when it does that, it's going to push down on our m1. And when that happens, it's not going to cause this whole system to accelerate. Instead, the normal force is just going to get bigger to counteract both of those gravitational forces. What we'd have then is that our sum of forces in the y direction is still going to be equal to 0, again, assuming the table doesn't break or gravity turning negative and flipping direction, and everything going up that time. We would just have the sum of forces equal to 0, no acceleration in the y direction. And then the forces that are going to be acting in the y direction, you can see from this, are going to be FG1 vector plus, those are vectors, so FG1 vector plus FG2 vector. Not F2G, FG2, there we go. This will be equal to a 0 vector, and now we can go from vector world to scalar world, and we can say that FG1 is negative FG1 scalar minus FG2 scalar. Oh, and I also forgot a normal force vector as well. We'll have a plus a normal force. All right, I can add FG1 and FG2 to both sides of my equation. So I'll do that, FG1 plus FG2. Over here, we get a plus FG1 plus FG2. And what I would do then is write my next step as normal force is equal to FG1 plus FG2. I know the equations for FG1 and FG2. That's M1G plus M2G. And then I can maybe factor out a g or something like that and get my normal force is equal to g times m1 plus m2. At this point, we could define a new mass. We call it maybe capital M, say it's equal to m1 plus m2. And I can say that my new normal force is now equal to g times the combined mass of both objects. And this is really, really important because I can think of it as if I take a 15 kilogram mass and I put it inside of a bag and I give it to you and you hold it and you say, oh, that's 15 kilograms. And I go, okay, well, is it a 5 kilogram mass and a 10 kilogram mass? Or is it a 15 kilogram mass? Or is it some combination of other masses? And you wouldn't really be able to know because it's inside that bag. And that's what the table kind of feels too. It doesn't see that they're two different objects. It sees that they're one combined mass acting with these forces on it, and it exerts a normal force to return and to keep that acceleration at 0. So this is another way that we could have our normal force change. Last one that we have for changing normal forces or weird stuff with normal forces is this. Sometimes our normal force can be significantly less than gravity is. Let's say that I pulled on this thing with an upwards tension force. Say that this angle is 70 degrees. And I know that there's a gravitational force pointed down. And this thing has mass. So we'll say our mass is equal to 25 kilograms. And that gives us a gravity force, Fg, equal to mass times gravity, which is 25 kilograms times our g constant, 10 meters per second squared. Multiply that and I get 250 newtons as my force of gravity, acting down. But let's say that I exert a tension force on these objects, as well as that normal force due to the surface. And let's say for argument's sake that I was able to get maybe a Newton meter or something and pull on this thing, and I measured my tension force, the overall tension force, as being somewhere around maybe 585 newtons. So I know my tension force, like the magnitude that's pointed in the direction of that tension force vector. And there's also going to be a normal force. And I'm drawing it pretty small, and it's really, 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 really obvious that that normal force is much less than the force of gravity. But how would this come about? Let's look at our Newton's first law statement for the y direction. So sum of forces is equal to, in the y direction, is equal to 0. Again, these are vectors. And the forces acting in the y direction, if we just look at them, we can say that there's a normal force vector, there's a tension force vector that acts in the y direction, and then there's this force of gravity vector, still equal to the 0 vector. The normal force, if we pull out, let's go ahead and define a coordinate system as well. We should do that every time. Positive to the right, positive x to the right, and positive y to the up. So our normal force vector is going to be in the positive direction, n, and we will add a tension force in the y direction to that, because the y component of tension is going to be positive, and the gravity force, that's going to be pointed down, so it will be negative. This is our new equation. We've gone from a vector equation to our scalar equation by pulling out that negative sign from gravity and removing our bars from over the top of our quantities. We are trying to calculate this normal force. So my normal force, I can just subtract a tension force in the y direction and add a force of gravity to both sides. So minus Ty plus Fg. And I get that my normal force is equal to my force of gravity minus my tension, or my y component of my tension force. Now we're going to have to put some stuff together and do a little bit of critical thinking about how I can combine things and how I can use the algebra I learned in math class and stuff like that. First thing that we're going to do is we're going to make that substitution for Fg. We know force of gravity is equal to mg. Then if I look at my tension vector, it points off in this direction somewhere, 70-degree angle. And so my x component is that, and my y component will look like this. And this is my Ty, and this is my overall tension. And so you can see that Ty is going to be the opposite, and so that will be sine. And so this is one of those weird situations where we might have a sine and a cosine, like maybe a tension force will give us a cosine, for our x direction, and then the gravity force, if we're on an inclined plane as well, might give us a sine. And so it could happen that we'd have two different angles we have to deal with, but probably not very often. So our tension force in the y direction, we can calculate that as being tension force times sine of that angle theta. And I can put that in for Ty, and I get my normal force is equal to mg minus T times sine theta, where tension is our, or T is our tension force, the overall magnitude of our tension force, and theta is that 70-degree angle. Okay, last thing to do is really just plug some numbers in. We know our mass is 25 kilograms. We know G is 10 meters per second squared. Force of gravity is 215 newtons. And our tension is 585 newtons. So we'll go ahead and just plug in our let's see here, our 250 newtons